So if you observe here, h tan 1 minus h tan 2 equals to k. So what is the condition for which both values will be equal? That is k should be equal to 0. Otherwise अगर k 0 नहीं है तो tan 1 and tan 2 दोनों सेम नहीं होंगे. That is tangential components of the field intensity h वो equal नहीं होंगे when k is not 0. कुछ value रहेगा. If k surface is current free, अगर वैसा है, that time both will be equal. Equal का मतलब क्या है? Here I have given both are not equal. Under the condition you have some k. Okay. If you have k equals to 0, both are equal. Means, in other words, we say that tangential components of h are continuous. Okay. We use the word continuous or discontinuous. अगर सेम वैल्यू इक्वल है दोनों भी, इक्वल मींस सेम ही रहेगा, एक मीडियम से दूसरे मीडियम में जब फील्ड एंटर होगा थ्रू दिस बाउंड्री उसको अफेक्ट नहीं होगा. tangential component won't get affected. It is continuous, provided k should be equal to 0. But otherwise I have given here it is both are not equal, so it is discontinuous. Now taking this equation, if I substitute, we know already b equals to mu h. So if I use this, if I want b from this, substituting this, what will be h equals to? H is b by mu. So I'm substituting that b by mu for both medium 1 and 2. So tan 1 by mu 1, tan 2 by mu 2 is equals to k. So how can I write this? Both values of h tangential components are equal, or equal matlab continuous, provided k is 0. And what about b? b uska ulta hoga. If this is continuous, the other one will be non-continuous. You can observe यहाँ पर अगर मैंने k का वैल्यू सब्स्टिट्यूट कर दिया 0, ओके, ये सेम है, ये जो इक्वेशन हमने लाया है यहाँ पे, I am substituting k as 0. Mathematical analysis you do, 0 होगा, so this is equal to this. Okay, so b tan 1 and tan 2 equal नहीं होंगे because you have permeability values mu1 and mu2 in the equations. So अगर मुझे दोनों को इक्वल करना है, mu1 and mu2 दोनों सेम होने चाहिए, मतलब मीडियम सेम होना चाहिए. बट व्हाट वी हैव कंसिडर्ड इन आवर फिगर, देयर इज वन बाउंड्री, यहाँ पर एक मीडियम है विद परमिएबिलिटी mu1, यहाँ पर mu2 है. सो जब आप दो अलग अलग मटेरियल्स ले रहे हो जिसके परमिएबिलिटीज अलग अलग हैं, अंडर दैट situation b, that is flux density, b tangential component, they are not continuous, they are dependent on mu, they are discontinuous. जब भी एक मीडियम से दूसरे में, एक मटेरियल से दूसरे मटेरियल में फील्ड एंटर होगा, these tangential components are discontinuous. H tangential components are continuous provided k is 0. This is about tangential component. Now let us talk about the normal component. So we have to discuss two different components. You can observe the figure here. Initially we have stated we have to discuss tangential and normal. Tangential के लिए हमने figure में ये rectangular loop consider किया हुआ है. Now to get the normal component, we will make use of this cylinder, imaginary Gaussian surface in the form of a cylinder. Okay, you may ask the question, why we have considered these surfaces only, these shapes only? You know, Gaussian surface can be of any irregular shape, but this will make our work easier. Otherwise इस cylinder के बदले में you can use any shape, because you can apply Gauss's law to any irregular shape. Okay, just try to recall Gauss's law applications, what all we have done. Okay, cylinder is one of the applications. Now, applying the boundary conditions to find out the normal component. Just like just now we have seen tangential component में B is a tangential component and H टेंजेंशियल कंपोनेंट कंटिन्यूअस है या डिसकंटिन्यूअस है, सेम रहेंगे या अलग अलग होंगे व्हेन दे ट्रैवल फ्रॉम वन मीडियम टू अनदर मीडियम. सिमिलरली नाउ नॉर्मल कंपोनेंट का बिहेवियर कैसे होगा when they enter from one material to another material, how these fields will behave, whether they'll remain same, whether they are continuous, or whether they discontinue, whether they change their behavior, we have to see. So for that, consider a closed Gaussian surface in the form of a right circular cylinder. Right circular cylinder means its axis is perpendicular. Perpendicular to what? The surface considered. No doubt, जो हमने surface consider किया है वो straight line नहीं है. It is somewhat little curved, okay, bent है. But right circular cylinder यहाँ पर हमने लिया है. इसका मतलब उसका axis and ये जो हम consider कर रहे हैं interface, ये part, ये दोनों perpendicular होंगे. Okay. Let the height of the cylinder is delta h, and it is placed in such a way that half of the cylinder part is lying in medium 1 and half of the part is lying in medium 2. It is just like a rectangular loop. How we have considered in the figure for tangential component. हमने कैसे place किया था loop को? Its half part is lying in one medium, half part is in one more medium. तो अलग-अलग materials अगर हैं तो ये जो हमने कंसिडर किया हुआ है एरिया, in that half part is in one medium, half is in another. Similarly, observe here, half of the cylinder is in one medium, half of the cylinder almost, okay, or half of the cylinder is in another medium. We have assumed that इसका surface area जो है it is delta S, okay. And then what else? इसका height जो है cylinder का we have considered delta H as the height. Okay, now as I said, right circular cylinder, axis of the cylinder is perpendicular to the surface. Now as we are using Gaussian surface here, let me use Gauss's law in order to find the normal component. What Gauss's law we have studied, just try to recall in your module 2, we have seen d dot ds is equals to this flux, displacement flux. I think आपने ऐसा लिया था, right? Psi or q. This was Gauss's law, not like this. So this is Gauss's law. This is applicable to electric field. When we talk about the flux density, electric field intensity, dE, everything is for electric field. But now we are discussing everything with respect to the magnetic field. That's why we have to correspondingly take the analogy. For D, we are taking the analogy of B. And for E, we take the analogy of H. Remember this. B के लिए हम B लेते हैं, E के लिए we take H. In case of magnetism, we make use of this. Try to recall when we were dealing with, I think, scalar and vector magnetic potential, we have come across this equation. This was actually flux phi is equals to, magnetic flux phi equals to surface integral of BDS. Try to recall this. From this, inside the what considered surface, we had taken the size equals to 0. So this integration of B dot ds equals to 0. This is your Gauss's law in point form. This is for magnetic field. ये जो हमने लिखा है B dot ds equals to q, or probably I think आपने class में ये लिया है del dot D equals to rho v, Maxwell's first equation. Okay, that is one equation we have studied in electric field. But when we talk about magnetic field, we have to replace the analogous terms. So this is your Gauss's law for magnetic field. So taking this surface integral of B dot ds equals to 0. Now this integration for our considered Gaussian surface we have to solve. What is the considered shape that we have chosen? It is the cylinder. And please try to recall in theory part we have seen जब भी हम एक सिलेंडर के लिए when we consider different surfaces, try to recall Gauss's law applications. Totally 3 different surfaces will come for the cylinder: top surface, bottom surface, and ये जो है lateral, what we call, the complete area जो होगा, that. So the totally 3 different areas will come in this cylinder. So we have to calculate this Gauss's law का जो left hand side है for magnetic field, surface integral of B dot ds, we have to calculate this for 3 different integrals. एक होगा top surface, एक bottom होगा, and एक lateral होगा. Now out of these 3 integrals, let's see which one we have to keep and which one will vanish. Suppose this is your boundary, and here I'm considering a cylinder. Okay, top surface है, bottom surface है. The height of the cylinder that we have considered is delta H. We are interested in the behavior of B and H at this boundary. Suppose again let me take 1 2 line. ये आपका interface है boundary पे. Okay, what will happen when I start decreasing the height? ये cylinder को कैसे affect होगा? How when I start decreasing the height delta H, my cylinder will start shrinking. Something like this. छोटा होते जाएगा उसका एरिया. ओके, नो डाउट ये जो शेप है इसका रेडियस है वो सेम रहेगा. ओके, आई हैव ड्रॉन ऑल रेडियाई डिफरेंटली, बट प्लीज मेक श्योर कि उसका रेडियस सेम हो. जस्ट लाइक अर्लियर डेल्टा डब्ल्यू हमने सेम रखा था, सिर्फ हमने डेल्टा एच को टेंडिंग टू 0 किया था. सो हियर ऑल्सो इफ आई स्टार्ट डिक्रीजिंग द हाइट ऑफ द सिलेंडर, it will become smaller 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 and it will coincide with this line 1 2. Top surface and bottom surface दोनों भी ये ऐसे मूव होगा, ये ऐसे मूव होगा, दोनों भी ये 1 2 इंटरफेस लाइन पे आके कोइंसाइड हो जाएंगे. समथिंग लाइक दिस. एक सिर्फ सिंगल सरफेस ऐसे मिलेगा मुझको. Try to imagine this. Okay, I cannot draw it here. एक सिलेंडर है, उसका हाइट व्हेन आई स्टार्ट श्रिंकिंग द हाइट टू 0, इट विल बिकम स्मॉलर एंड स्मॉलर एंड स्मॉलर, एंड टॉप एंड बॉटम सरफेसेस विल कोइंसाइड. आपको सिर्फ एक सिंगल सरफेस मिलेगा यहाँ पे ओवर दिस पॉइंट 1 2 इंटरफेस पे. ओके, यहाँ पे अगर आप ऊपर से देखेंगे तो वो टॉप सरफेस होगा, नीचे से देखेंगे तो इट विल बी बॉटम सरफेस. दे बोथ विल कोइंसाइड. So this is the effect when I start decreasing the height of the cylinder. So if I do that, out of the 3 areas that we have to calculate, we should not go for lateral. क्योंकि जब हम height कम कर रहे हैं, आपका lateral area बचेगा ही नहीं. What will happen? It will simply, become, ये अगर आपका interface है, finally आपका पूरा cylinder जाके सिर्फ इतना एक surface बच जाएगा top पे. ऊपर से देखोगे तो वो टॉप होगा, नीचे से देखोगे तो वो बॉटम सरफेस होगा. सो देयर इज नो लैटरल एरिया अवेलेबल. सो दिस इंटीग्रेशन नीड नॉट हैव टू बी कैलकुलेटेड. सो ओनली वी हैव टू बी बॉदर्ड अबाउट टॉप सरफेस एंड बॉटम सरफेस. दैट्स इट. Okay, now let's see what are the values for these two. So if we are interested only at the boundary, so delta H we will try to shrink it to 0. जब delta H कम हो जाएगा, lateral surface will not exist, only top and bottom surface will contribute. You can see मैंने यहाँ पर फिगर ड्रॉ किया है. तो अगर यहाँ पर आप ऊपर से देखोगे तो ये टॉप सरफेस दिखेगा सिलेंडर का, नीचे से it will be bottom surface. Only one surface will be available, a thin slice of a round potato, you can imagine, one single slice. So what will be this top surface? Some flux density value will be there. So let me take it as Bn1. N indicates we are interested in normal component. Earlier we were interested in tangential, so we have used TAN. Now we are interested in normal, so you can use NORM or N. No issues. So Bn1. Why it is N1? क्योंकि top surface आपके first medium में है. Observe here. Let me quickly show you. Yeah, observe here. top surface is present in the first medium, bottom surface is present in the second medium. That's why I have used N1 and N2 as the subscripts. So using that, for top surface, it is some flux density value, and area we have assumed it as delta S. This is top. Now for bottom, it will be, sorry I missed it here, it should be negative. क्योंकि when I use the flux, you can see यहाँ पर एक surface है, okay, area of cross section. If the flux enters from bottom surface, it leaves from the top surface, right? अगर flux entering आप positive लोगे, flux leaving आप negative लो, और flux entering आप negative ले रहे हो, flux leaving positive लो. In either cases, any one value is negative. So it is up to you which one you want to take. Generally, flux entering we take positive, flux leaving we take negative. So ideally speaking, ये negative होना चाहिए, ये positive होना चाहिए. Fine. So otherwise, it's up to you. When I add both top and bottom, as any one is negative, I'm using the second bottom as negative. Bn1 delta S minus, it is actually plus, but since there is a negative sign, flux entering and leaving, both are opposite to each other. So it is minus Bn2 delta S equals to 0. So if that is the case, just equate them. ये negative है, ये term को आप RHS में ले जाओ. Both are equal, so delta S gets cancelled. So Bn1 is equals to Bn2. Means B, flux density, N, normal component, both are equal. Means whenever you have two different materials which are having two different permeabilities, under that, when the field travels, when the field moves, the field is a continuous, flux density is a continuous, normal component. Normal component of the B is continuous at the boundary. Okay, I am talking about B now. Let's see what about H, because B equals to mu H. From there, let me substitute it here. Mu1 Hn1 is equals to mu2 Hn2. So what is Hn1 by Hn2 equals to mu2 by mu1. So whether H1 and H2 can be equal, they cannot be, क्योंकि दोनों मीडियम अलग अलग हैं. So ये दोनों अगर सेम है तो probably आपको यहाँ पे 1 मिलेगा. That time Hn1 normal components of H are continuous, provided material सेम होना चाहिए. बट अगर आप दो अलग अलग मटेरियल्स के थ्रू फील्ड जा रहा है, तो फ्लक्स डेंसिटी का नॉर्मल कंपोनेंट जो है, इट इज नॉट कंटिन्यूअस. ये रिवर्स होगा. जो हमने टेंजेंशियल में देखा था, उसका कंप्लीटली रिवर्स यहाँ पे नॉर्मल कंपोनेंट में है. लेट मी रिकॉल दैट. When we talked about tangential component, in tangential component, B, you can see B was discontinuous. It was not continuous B, क्योंकि वो permittivity पे dependent था. But H was continuous. H tan 1 is equals to H tan 2, provided K is 0. That we had given the condition. H is continuous, B is discontinuous. ये tangential के लिए. But when we talked about normal component, ulta hai. B is continuous, H is not continuous or discontinuous. Okay. So these are the two boundary conditions that we have seen: tangential component and normal component. The next concept is, I'll just give you the brief. It is the same, sorry. Then I'll just introduce you about what is this next concept. We are going to study about magnetic circuits. It's not a new concept for you. You have already studied magnetic circuits, probably in your electrical engineering background. There you have seen some of your transformers, generators, motors, those are some of the examples of magnetic circuits. So we won't be getting into those details of all, but just a brief introduction of the overview of the concept we will be looking into here. Okay, we won't be studying generators, motors, transformers. No, just as in एक magnetic circuit क्या है, how can we take the analogy of magnetic circuit with electrical circuit? आपने network theory में पढ़ा है, you have studied NT, you have studied how to analyze any electrical circuit. You come across resistors, capacitors, you know, many components. You come across some what generate this voltage source. You find out the currents. Those are the electrical circuits which you have already worked on them, you have studied them in the laboratory, you have studied in your network theory. But coming to magnetic circuits, can we have an analogy? Let's see that. Okay, we can see I have given one analogy of electrical and magnetic circuits. Before that, some terms I have just listed here. In magnetic circuits, we determine magnetic flux. हमने electrical circuits पढ़े हैं. Electric circuits we have already studied. There we find current and voltage, right? हमको V and I are very important terms there. But in magnetic circuits, magnetic flux, I think phi. Phi is important for us, and magnetic field intensity. Magnetic circuits, they are analogous to electric circuits. Examples of magnetic circuits are transformers, generators, motors, etc. Now, some of the common terms that you come across in magnetic circuits are flux, flux density, and I think MMF, just like EMF, electromotive force. You come across magnetomotive force here, MMF. What else? Yeah, these many terms, basic terms you come across. We will study those definitions. Now, you have studied EMF, that is electromotive force in electric circuit. And what is the unit? It is volts. But when we talk about magnetic circuits, it is magnetomotive force. And the unit of magnetomotive force is ampere turn. This is one analogy, okay? When I compare E and EM, electromotive force, EMF, it is analogous to magnetomotive force. In electric circuits, we talk about current, electric current. But magnetic circuits, we talk about magnetic flux. Current amperes में measure होता है. Flux is measured in Webers. Then electric circuits में resistance होगा. Ohms में measure होता है. I don't know how you pronounce this symbol. It is something Greek letter, something, okay, R kind of thing. This is the symbol. It is called a reluctance. In magnetic circuits, it is called reluctance. And the unit of reluctance is M, and that is meters per ampere turn. Electric circuits में conductivity is important parameter, which is the reciprocal of, we call it mho, right? Reciprocal of resistivity, what we call it. So it is mho. In magnetic circuits, this is analogous to mu, permeability. जैसे conductivity of the medium वहाँ पे है, electric circuits में, magnetic circuits में permeability plays an important role. Conductivity का unit mho है, MHO. Permeability का unit ampere turn per meter square. Now, coming to one more important analogy, Ohm's law. You know this, V equals to IR, right? I have written E, you can take V equals to IR, or what P equals to VI, right? Ohm's law you have studied. So just like Ohm's law, here in magnetic circuit, important is both. You'll come across both Ohm's law as well as Kirchhoff's law. Here it is magnetomotive force, F equals to phi into R. You know current I is analogous to magnetic flux phi. Okay, and ये R नहीं है actually, it is reluctance, right? So Ohm's law is V equals to IR. Here it is magnetomotive force F is equals to phi into R. Reluctance, sorry. Let me pronounce it as R only, but it is a Greek letter R. And R equals to rho L by A. You know this already. R is in terms of rho L by A. Rho is resistivity, or it can be even in terms of conductivity. But here reluctance is L by mu into A. I think ये सभी basic equations हैं, आपने electrical में पढ़ा होगा. And whenever you come across some more than one resistances, you add them in series. Okay, series resistance, you simply add them. अगर parallel में है तो you take 1 by, ये आपको पता है how you find the equivalent resistance. Similar to that, even in magnetic circuits also you come across series reluctance and parallel. वो similar है concept, आप add करते हो या फिर you take the 1 by R1 reciprocals, adding the reciprocals. So this is the analogy between electric circuit and magnetic circuit. So in the next session, we will continue with some of the basic terms, definitions that we come across in magnetic circuits. That is, flux का मतलब क्या है? Then B. These are all very common terms. Just definitions we will look into, and after these definitions, we will go for important derivation, that is energy stored in a magnetic field. Prove that the energy stored in a magnetic field is given by so and so. So this is one important derivation. These three things, basic definitions, magnetic circuit एक example लेके how what are the basic things are there, basic terms are there in that circuit, we will see, and important derivation we are going to do, energy stored in the magnetic field. And if the time permits, we will see what do you mean by self inductance and mutual inductance. ये दोनों आपने पढ़ा है already, self inductance and mutual inductance. So we will see what is that, right? That we will cover in the next session.